Hello everyone and welcome back to my channel. In the last lecture, we started a discussion on the convection diffusion equation. Taking a general case of one-dimensional steady convection diffusion, we introduced the finite volume method. So we took a step away from the finite differences, and I told you how you can consider a finite volume around our point of interest P. And using that property of the control volume or the finite volume, we arrived at the discretized version of the governing equation. So in a nutshell, we had the governing equation, we integrated that equation, and we use this control volume, or we use this finite volume to come to that discretized version. So today I would be talking about certain kind of schemes that are used in such problems where we have this convection term. The whole complexity of Navier-Stokes equations actually arrive from this convection term, because that's where the non-linearity of the system actually lies. So it's very important that we understand how we can deal with this non-linear convection term. So in the lecture today, I'll tell you about two very popular schemes, the first of them being the Upwind scheme and the second being the quick scheme. So we'll see how we can use these schemes, or what exactly is the fundamental behind using these schemes for the convection term. So before I go into that, I'll give you a brief recap of what happened in the last lecture. So let's jump right in. So in the last lecture, we had this particular equation. So we had this equation here, which is d over dx of rho u phi equal to dy dx of tau d phi over dx. So on the right side we had the diffusion term, and on the left side we had the convection term. And after we integrated the entire equation on this control volume, which is of the importance here, so we had this control volume around point P, and we integrated this equation over that, and using that we came at the integral version of the governing equation, which is written here. So after solving the integral, we came to this particular step. I'll call this as, let us say, equation capital 1. So capital 1 equation was without any assumptions. So we took the governing equation as it is, we integrated it over the control volume, and we arrived at equation 1. So until equation 1, we didn't have any kind of assumptions in the picture. After step 1, we introduced this assumption of piecewise linear function, or we assume that the function phi or the variable t or whatever it is, it varies linearly between any 2 points. So we said that the function phi, it was varying linearly between P and capital W, and similarly it varies linearly between P and capital E. So using that, we come to this particular big equation, and we defined something called as F, that was related to convection, F being equals to rho times U, and we introduced a diffusion term as tau over delta x. I'm sorry, it should be gamma over delta x, not tau. So I'll write that particular equation again. So we had this as the general solution of the convection diffusion equation. And if I want to show you what the solution of this particular equation, that is the convection diffusion equation. So we had the equation being the first derivative of rho u phi is equals to the first derivative of gamma times d phi over dx. So we had a convection term and we had a diffusion term. So let us consider a 1D domain, because it's a 1D situation. So let us consider a domain which is at x equals to 0 and x equal to L being the endpoints. And we say that the phi is phi 0 at x equals to 0 and phi is phi L at x equal to L. Now it is very easy to solve this particular governing equation, because it's ordinary differential equation. It's not even a partial differential equation. It's an ordinary differential equation in one variable x, and we have one variable phi which is of our interest. So if you do the mathematics, it's very easy to show that the solution for phi is written in this particular form. So we have a parameter called as capital P, which I'll be showing you very shortly what that is. The P is called as the Peclet number, and that is given as rho UL divided by gamma. So the Peclet number is a ratio of the convection to the ratio of diffusion. So if we look at this particular equation, if this particular solution, and if I want to show you what the solution of this particular problem, that is where at x equals to 0, so we have this on x-axis and this as phi axis. So at x equals to 0, we have this particular point which is phi 0, and let us say this is as phi L, and let us say that this is L. So that we have these two as the boundary conditions. So I want you to understand how the Peclet number is going to affect this particular solution. So the Peclet number is defined as rho UL over gamma, or the convection over the diffusion. So Peclet number 0, it implies a pure diffusion problem because the magnitude of U would be 0, right? So when the Peclet number is 0, it means the convection term is 0 and we have only diffusion in the problem. And coincidentally, we have done this, right? We only considered the diffusion equation in the past, and we saw that the solution of such a system is linear, that the temperature was varying linearly from one end to the another end. So if the Peclet number is 0, we know that this particular problem would have a linear solution. Now let us say that this is x equals to 0 and this is x equal to L, and the corresponding U, or the convention, is that the U is positive if it's in the positive x-axis and U is negative if it's in the negative x-axis. So I want you to have an intuition of, let us say we have a low temperature here and a high temperature here, and think about this for a moment. If you raise the temperature here for a while, and if you have a velocity that is flowing from this direction to this direction like this, right? So you can imagine that as soon as you raise the temperature here, it would be convected from this point to this point because of that velocity. So the convection would be taking place here, and all the property that is generated here would be transmitted there very quickly. So whenever the U is greater than 0, the properties here, it would almost shift over here, right? So the corresponding variation of phi on the plot here would be something like this, right? So let us say this is for P is greater than 0. So P is greater than 0, it is due to the fact that the velocity magnitude is greater than 0. And similarly, when P is less than 0 or the U is in the negative direction, it means that the variables here are going to be very rapidly transferred or convected to the variables that is on the x equals to 0 side. So what I'm trying to say here is that for P less than 0, we would have a situation like this. And the extreme cases are when this Peclet number is very large, or you can think of that this is a very strong convection. So as soon as something happens here, it reaches all the way up to here. So we would have almost no variation until here, and then all of a sudden there would be very large variations. Remember that the boundary conditions are always fixed. This is always phi 0 and this is always phi L. The only variable here is the Peclet number, and that determines how quickly or how slowly this change is going to happen. So when the Peclet number is very large on the positive side, the variation here would be very slow because it's convecting everything downstream. But as soon as it reaches here, there would be a very sharp gradient across this, right? So for very large Peclet number, I would almost have a variation like this. So this is p greater than 0. And similarly, for a very small Peclet number, on the negative side, we would have something as shown as this. So this is the ideal or the exact solution of the problem. Later, we would be trying to find numerically whether our schemes, can they actually provide this solution or not. So first, I would talk about what is called as the Upwind scheme. So all of these schemes, they are to deal with the convection part. So the diffusion term remains as it is, will not touch the diffusion part, will only deal with the convection part. And all of these schemes, they provide a way to find the convection F values. You remember we have these F small e and F small w for the faces of the control volume. And we want to see how this convection coefficient or how this convection strength is actually given by these particular schemes. So I'll first draw the same control volume again. So we had this P, we had this capital E and capital W, and we had our control volume where we had this small e and small w. We took our governing equation and we integrated it, remember? So we had something like Fe phi small e minus Fw phi small w equals to diffusion. I'm not going to touch the diffusion term because that's not of my interest. So previously what we did was we assumed that the phi was varying linearly. Let us say this is capital P, this is capital E, and so this would be the small e. So we said that because the phi was varying linearly between these 2 points, therefore the phi at small e, it would be half of or the average of these 2 phi. In the Upwind scheme, what we say is the value of phi at small e, it would be the same as the upstream value. So what that means is, let us say if the flow is going from left to right, so it means that phi at small e is the same as phi at capital P. So remember that Peclet number thing again. It assumes that if the Peclet number is greater than 0, it means that, or if the flow is going this way, the Upwind scheme assumes that the property here is actually being transferred from the capital P point. So it doesn't say that the phi small e is the average of these 2 numbers. It is very direct in the sense that it says that the phi at small e or the control volume phase is the same as the upstream side because the flow is going this way. So this is the upstream side, this is the downstream side. So for this particular point, this point is the upstream point and this is the downstream point. So that means that phi at small e is equal to phi at capital P. So if I want to find out the phi at small e, we say that it's equal to phi at capital P if the u is greater than 0, or if the u is less than 0, it means the flow is going this way, then the upstream point would become phi at capital E. So whatever the control volume phase value is, it's the same as the variable at the upstream point. So we have to decide what the upstream point is. And to put this in, so we have this function that says that if the u is greater than 0, we had certain value, and if the u is less than 0, we have another value. So now we want to put this particular problem here, right? So we can't use this conditional statements here. So what we do is we introduce a maximum function that is equals to these large brackets x and y, and it returns whatever. So this is equals to whatever the maximum of those 2 number is. So if this is, if let us say x is greater than y, then it returns x, and if x is smaller than y, then this function would return y. So based on that, we can write that phi e, this is equals to phi p, the maximum function of fe comma 0. So now I have converted this u. You remember that fe is nothing but rho times u small e, right? Minus phi e minus phi small e comma 0. So now we want to verify whether this particular statement is equivalent to this statement here. So when the fe is greater than 0, it means ue is greater than 0. So when fe is greater than 0, this particular bracket would simply become fe, and this particular bracket, because the fe is greater than 0, then minus fe would be a negative number, and this bracket would become 0, and this whole quantity would become fe times phi p, right? And we said that when fe is greater than 0 or when ue is greater than 0, the phi e should be equal to phi p. So this particular solution, this should be f small e. So fe phi e, it becomes fe phi p. I hope you understood this. And similarly, the fw phi w, it would become phi w, and the maximum of fw comma 0 minus phi p minus fw comma 0. And when we want to write the governing equation, it would also take the same form of ap phi p equals to ae phi e plus aw phi w. So at this point, I don't want you to dive very deep into the mathematics that is going on behind the scene, but I want you to have a physical understanding of what's going on. So the idea here was the upwind scheme, it doesn't assume that the function is varying piecewise linearly between the 2 points. It rather takes the upwind value as it is for that particular function. So that is one way in which we can simplify the convection term and could arrive at the governing equations discretized version. So we would be looking at the exact coding part of the upwind scheme or the piecewise polynomial linearly scheme later on. But at this point, I want you to give an overview of what exactly would be going on and how we would be doing it in MATLAB later on. The next scheme that I want to talk about is called as a quick scheme. And if you have used any kind of CFD software, I hope you would have read these somewhere during when you were initializing this problem or finding the setup for your problem. So these kind of schemes are very commonly used in CFD, and that is why I'm only sticking to these very popular schemes. Although there are a lot of schemes that can be used, but that's too many to cover, and I want you to understand only the very popular or very robust schemes that are very commonly used. So now let us look at the quick scheme. So the quick scheme here. So I'll give you what it stands for, and with that also you'll get an idea of what it would be. So the quick scheme stands for quadratic upwind interpolation for convection kinematics. So you can see that in the name itself we have this convection kinematics. So all these schemes are meant to deal with the convection term, and in quick scheme we say that it's quadratic upwind interpolation. So it's still some sort of interpolation which is based on the upwind scheme, but in the upwind scheme we were very direct. We said that the upwind value is exactly the same, but in quick scheme we want to improve the robustness of the scheme, so we consider more points on the upstream and the downstream side, which I would be showing you later. So let us say we have the same problem. We have this P, we have this capital E and capital W. So let us consider the case of when U is greater than 0. So we had, let us say we want to investigate this small e point. So the idea of upwind scheme is very simple. So the idea of quick scheme is very simple. We consider 2 points on the upstream side and 1 point on the downstream side. So in this case, because the flow is going from left to right, so we have capital P and capital W on the upstream side, and we have this capital E on the downstream side. So we assume that the function varies quadratically, that is the phi is in the form of ax squared plus bx plus c. So the phi would be varying something like this, where we know the value of the functions, right? So we know that this is phi capital W, this is phi capital P, this is phi capital E, and we want to evaluate what is phi at small e. So this particular quadratic form, we know that there are certain boundary conditions. We know that at x equals to xw, or if we assume that this is x equals to 0 or x equals to 0, we have phi equals to phi w. At x equals to xp or small h, which is the grid spacing, we have phi equals to phi p, and we have another variable, that is x equals to xe or 2h, we have phi equals to phi e. So we have one equation for phi which is quadratic in nature, so it only needs, although it only needs 2 indifferent boundary conditions or boundary points, but we have more than that, so we can easily determine these coefficients a, b and c. So if you solve this, you can get a is equals to phi w minus 2 phi p plus phi e divided by 2h squared. You can get b of the form of 4 phi p minus phi w plus 3 phi e divided by 8, and the c is simply equals to phi w. So now we have the value of a, b and c. We know that the phi varies quadratically between these 2 points, these 3 points, and the phi small e, it lies somewhere in between. So using this quadratic function, we can interpolate for phi e. So we know that for phi small e, it means that x equals to 3h by 2, right? So if this is the origin, then this particular distance is 3h by 2. If you put that, you can obtain that phi small e is 6 phi p minus phi w plus 3 phi e divided by 8, right? So in the quick scheme, we use these 3 points around the control volume phase to obtain this phi small e. So coming to the sort of conclusion here, for the first part, for the central difference or for the piecewise polynomial scheme, the phi small e was given as the average of the surrounding points. In the upwind scheme, we considered the upwind direction, and we said that the phi small e is the same as the phi at the upstream point. In the quick scheme, we took 2 points on the upstream side and we took 1 point on the downstream side. We fitted this quadratic polynomial and we interpolated for phi small e. Similarly, let us say we had these same points. We had this P, E and W, and if the flow was from right to left, then it means that we had to consider another point, this east-east. So if we want to evaluate the same small e, because one upwind point is capital E, we needed another upwind point which could have been phi capital E, and the downstream point would be capital P. So in this particular case, the expression for phi e then would be 6 phi e minus phi double e plus 3 phi p divided by 8. I hope I've written this right. So for now, I would recommend you that you can practice how these phi small e are obtained for the quick scheme cases. Generally speaking, out of the 3 schemes, the quick schemes give you the most accurate measurements or the most accurate results. while it would take time because it has to evaluate a lot of parameters to get that phi small e. So we'll take a very particular problem where we know about the flow field, and using that knowledge, we'll try to get this estimate of how the phi is varying in the particular problem. So in the next lecture, we'll take example of a case where we know how the u varies, and using that knowledge, we'll understand how the variation of phi is obtained from these three schemes. So before coming on to that, I hope that you'll give yourself a hands-on on deriving these all these numerical schemes that we have considered so far. And with that, I believe that you can have a very good understanding firsthand of what these schemes really are. So I hope that you learned something today, and I'll see you in the next video. Thank you.